Hello and welcome to our presentation for selective laser sintering. Our group consists of Layton, Ashleigh, myself being Sidney, Hunter, and Orest. This term we've really spent a lot of time looking at all the manufacturing processes as we've gone throughout this course with the professor. We've looked at additive manufacturing, which was what we will display today. We've looked at molding, we've looked at sand casting. We looked at a lot, so enjoy this time as we describe to you selective laser sintering.
So, in the mid-1980s at the University of Texas, Dr. Carl Deckard and Dr. Joe Beeman pioneered the development of selective laser sintering, also known as SLS. This is a revolutionary 3D printing technology with the ambitious goal of transforming traditional manufacturing methods. This innovative process, patented officially in 1989, introduced a groundbreaking technique where a laser selectively fuses powders materials layer by layer. This marked the inception of a new era in additive manufacturing, offering unprecedented possibilities for creating intricate three-dimensional objects. Originally conceived with polymers in mind, the early applications of SLS focused on utilizing powdered polymers for the rapid prototyping of objects. However, the versatility of SLS quickly expanded beyond its initial scope. Today, SLS can seamlessly work with a diverse range of materials, including aluminum, titanium, steel, ceramic powders, elastomers, nylon, and much more. This adaptability has positioned SLS as a versatile and indispensable tool in the manufacturing landscape. Major industry players such as HP, Formlabs, Syntratech, and Prodways have not only recognized the potential of SLS, but have enthusiastically embraced it, incorporating technology into their manufacturing processes. This widespread adoption underscores the effectiveness and adaptability of SLS across various different sectors. What began as an innovative process in a small Texas laboratory has grown into a global influential technology. SLS has transcended its origins, now standing as an incredibly innovative method used by companies around the world. Its applications are diverse, ranging from creating gears, levers, and tool housings to crafting seatbelt buckles and frames for a wide variety of products. As we reflect on this journey, it's clear that SLS has not only evolved, but continues to shape the future of modern manufacturing.
Although you may not be familiar with the term selective laser sintering, I'm sure you have seen these technologies in the real world. Selective laser sintering is growing drastically on a market analysis. It has been found that in the year 2023, 3.21 billion is the market size and is expected to grow to almost 9 billion in the year 2028. Currently, some of the fields that are most commonly used for this method is aerospace and automotive. SLS is extensively used in the aerospace industry to manufacture lightweight yet structurally robust components. Aircraft designers leverage SLS to produce complex and intricate parts such as brackets, ductwork, and even structural elements. The ability to create parts with high strength to weight ratios is crucial in aviation, where reducing weight is vastly beneficial as it can help with improving fuel efficiency and overall performance, as well as the automotive industry, where I said that it is also used. Automotive industry has embraced SLS for the production of various components, from interior parts like dashboard elements to under the hood components. SLS is utilized to create lightweight, durable, and complex structures. Lightweight materials contribute to the enhanced fuel efficiency, making SLS an integral part of this field. Some of the most common forms of this technology that you may see is jigs and fixtures. You can see a few different types of this technology here on the screen.
So next we will jump into a case study, so a real life example of when you can see SLS. So we had talked about the creator. It was created or kind of founded at the University of Texas by Professor Joseph Beeman. And he has continued to work on SLS and really strive to make improvements in his design and his creations, and not only teaching his students but informing his school around him. University of Texas is really interested and spends a lot of time and money on any sort of 3D printing. And SLS is again another additive process. So Joseph Beeman really takes a lot of time to teach his students, his mentees, anybody around him really. And with that comes new developments and new ideas. And one being the implementation of prosthetics using SLS. You can see here on the left side of this picture is a prosthetic leg. So SLS can be used in additive manufacturing, and that one of them being prosthetic legs. And then you can see there on the screen, SLS is used in dozens of applications, from 3D printing medical devices, fully formed metal parts for airplanes, or even race cars. And again, printing fixtures can be used both in the industrial area, and then again, printing fixtures for the home or anything like that, or in your own home. And then again, SLS is particularly significant in prosthetic limbs because it is so customizable for prosthetics. So as you would guess, prosthetics, everybody has a different prosthetic and everybody has a different leg. So being able to be adjustable to the individual user of a prosthetic is really efficient and beneficial for anyone who has a prosthetic leg. And then again, it's not like it needs like 6 months to be printed or has really crazy wait times. They really can be quick adjustments and quick turnarounds for the patients or the users of the prosthetic legs. And then it also can take various materials. So they can print metal, they can print plastic, they can really use anything in SLS, which gives another benefit of there being lightweight material. So you wouldn't want a really, really heavy leg in a really uncomfortable leg in a prosthetic. So it is good that you can use other materials. And then again, it's specific needs to that person. It's whatever material would work best for them. And then again, just think of the future applications and future implications of SLS, whether it be prosthetics or new medical devices that aren't even created now. It's really important to look at the future when you're thinking of these methods of printing and methods of creating new things. Is it doesn't just create the things we have now, but future things that we didn't think we could even make. And that's all on prosthetic legs.
So to look into the considerations of selective laser sintering, in the landscape of additive manufacturing, SLS stands out with a set of distinct advantages and considerations that shape its applications across various industries. To go into some of the pros of SLS, SLS boasts high precision, allowing for the creation of intricate and detailed parts with high accuracy. The technology also produces durable parts, which are suitable for functional prototypes and a variety of end-use components. One of its notable features is tool-free production. SLS eliminates the need for traditional tooling and reducing associated costs outside of the initial investments. SLS also facilitates batch printing, enabling the simultaneous production of multiple parts within the build chamber, which is good for optimizing efficiency and reducing overall production time. To go into the cons of SLS, while SLS offers remarkable benefits, there are notable challenges as well. The high equipment cost is a significant barrier. SLS requires a substantial initial investment for businesses to adopt this technology. It is not cheap to get into SLS, but it is incredibly beneficial once you do. SLS is also considered an advanced concept which requires specialized knowledge and training for effective operations, which may result in a learning curve for users. The expensive operation of SLS is also evident in material costs, particularly with specialized powders, contributing to the high overall production cost. Additionally, the limited build size of SLS machines may restrict the size of parts which can be produced in a single print job. So while SLS is able to batch build different parts with high precision, it is limited by the cost and size of the tool. Batch building will not be effective for producing a large quantity of large parts, but it will be effective for producing a large quantity of smaller parts at a very high level of precision with minimal need for other tools and features outside of the more expensive material cost and the expensive upfront cost, which may take some time to get a good return on investment for the company and depending on what products they are manufacturing, the profit margin they're able to gather from them. So to look at some of the design considerations for SLS, designers can leverage SLS complex capabilities through creating intricate and optimized structures. The support-free design features enhanced design freedom, eliminating the need for support structures, which could be found with like common 3D printing and different additive manufacturing technologies, compared to SLS, where it sort of builds upon itself layer by layer without the need for support structures, as the layer before it is its own support structure. The diverse material selection in SLS also allows designers to choose materials based on specific performance requirements. So like we can do like polymers, steels, aluminums, different materials depending on what type of product we're trying to create. Lastly, SLS also supports prototyping and iteration, making it an ideal choice for designers to quickly iterate and test various design versions. As different things are modeled and produced, it's very easy to make changes very easily between different batches to try to get a part that is as good as possible. Similar to the 3D printing, once the part is made, it can be put in with like a minimal effort into the program, and a lot of different adaptations and iterations can be made in a quick amount of time. It will just be costly to train someone to be able to perform the functions that are needed. To look at the economic considerations of SLS, the initial investment in SLS machines can be high. This requires a strategic approach to justify the upfront cost. Material costs, especially those for specialized powders, need to be factored into the overall production cost. Labor costs are mitigated to some extent due to the automated nature of SLS processes, but skilled operators may be necessary, especially those with CAD training, and in the design of the initial components. Production volume is a key economic consideration, with SLS best suited for low to medium production volumes. The elimination of traditional tooling costs is an economic advantage, particularly for small batch productions. So for the economic considerations, it's easy to batch build small components, but if you're trying to build larger components, it may not be as economically feasible as other technologies are out there in the world for additive manufacturing. Now to look at the environmental considerations for SLS. SLS showcases material efficiency by minimizing waste through the efficient use of a powder bed. Energy consumption is a notable consideration, with efforts ongoing to improve machine efficiency and reduce the environmental impact. Material recycling is possible in SLS, contributing to sustainable efforts. Chemical exposure, particularly when handling powder materials, requires attention to ensure environmental and health safety. Proper PPE does need to be worn with SLS, as these fine powders can be incredibly dangerous for the operators working on them. So it's very important to consider like the HSC of the operators and ensure that there's proper safety techniques, proper venting, and proper everything to make sure it is a safe process. A comprehensive life cycle assessment also needs to be performed to provide insights into the overall environmental impact of SLS products. So to summarize the considerations with SLS, selective laser sintering presents a spectrum of advantages and considerations that extend beyond the technical realm into the realms of design, economics, and environment. These aspects collectively contribute to the decision-making process for businesses and designers exploring the potential of SLS in their respective fields. It is incredibly important to look at the different methods out there in the world and consider if SLS is good for you. Just because companies such as like HP, Formlabs, Cintric, and Prodways have been able to use SLS for their own products, whether it's making like tool housings, prosthetics, and much more, with a lot of like different ways to adjust for different users. It may not work for every single company, as there are very high upfront costs, and it will take some time to get a good return on investment for their products.
Our main takeaway from this project is how timely this manufacturing process is in our world currently. As we talk about the automotive industry, it is known that fuel efficiency is one of the major goals when it comes to any form of transportation. This large pro to utilizing SLS is also a really good option for us to be able to customize products, reduce weight, and make environmentally sustainable and economic products around the world. We hope to see selective laser sintering grow as it was predicted to allow for us to have a large breakthrough in the manufacturing world. Please feel free to reach out to us if you have any questions. We enjoy learning about this topic and seeing the timely products that are being produced in this technology. Thank you for allowing us the opportunity to be able to dive into this manufacturing process that is interesting to us as well as a great term. Here you can see any of the resources we use for our research for creating this project as well as our overall understanding of this technology. If you have interest in SLS in the automotive and industry fields, a lot of these resources gave a good background and information on these fields as well as some pictures and deeper understanding. Thanks.